Hello everybody. My name is Sun Yao Cheong. So in this video, I'm going to talk about diffusion models for text to image generation. So many of us have heard about that currently the AI is able to generate images from the text prompt alone. So the model that the algorithm we talk about is the latest generation, which is called diffusion models. So today this presentation will be give you an overview of this text to image generation architecture, the algorithms from that the evolution. We will first talk about the evolution of this text to image generation, and then we will dive into this diffusion model. So I will give an high level overview, so you at the end of this this video you'll be able to understand what is this diffusion model without without really have to know about the math details or coding. No coding is required. All right. So by the way, the slide here, the background here, this image is generated using one of the diffusion models that we will talk about in this slide. It's called DiscoDiffusion. You can also it's free, it's open source. You can go and download it and then use it to generate image from the text prompt. Okay. All right. So just before we start, I would like to just introduce myself. My name is Sun Yao Cheong. So I'm currently an AI consultant. So I do various of AI projects, short projects, and also some more longer term contracting. I do a lot of different type of project, from more machine learning, data science, to also deep learning. So my specialty actually is the deep learning, specialized in generative AI. I also wrote a book, and I'm currently doing a PhD. My research area now is exactly like this topic of this talk of this video. It is the text to image generation using AI, of course. So this is the paper, the latest paper that we wrote. So just to give you some idea about the paper, is that this is based on a transformer architecture. So in vanilla text to image, you can only use the text, the text to describe what your image look like. But we found that it is a bit constraining. So there are a lot of things that cannot be easily described in words, like the pose or like your camera angle, like how much you want to zoom in, zoom out. So that's why we add another modality, which is this pose. We use this pose as we have a novel method to encoding pose, which is not the conventional skeleton. So this is just for illustration. We use a pose and also text. So pose and text to image generation. So this one can faithfully describe the what the human model looks like. This one is the first sentence is on the left, the woman on the left, then the second one is the woman on the right. So the left one should wear yellow long sleeve dress. Okay, they're all wear yellow long sleeve dress, and the second one is a multicolor long sleeve tee. So this is it, and they all have the same pose as the pose. Okay, that we give them. So this paper have just submitted to a conference. It's under review now. Right. So first, I would like to give an overview of this evolution of this text to image algorithms. The first one really starts with this generative GANs, stand for generative adversarial networks. So it is a very popular algorithm or family of model that can create a very realistically looking images. So the year that I put in here is not the year of GANs, but more in the context of using GAN in text to image generations. So it started at around 2016, It after 2018, so there was not much, a lot of activities happened after this year. So I just put it a random, not random, just give you an idea of so what is the active period of this generation of technologies. So the one of the biggest limitation of GAN in this text to image is that in those early years, so the GANs are very limited to the data set. So they train on small data sets, and because of sorry. So one of the limitation of GAN is that it only for this one text to image only works on small data set that is kind of like constrained in a very narrow world. Like in the top row image we can see, so this one is from bird images. So every images have a bird in the center. So what are the differences are mainly in the colors of the the beak, their feather, their belly. So in that sense, so this GAN can do an okay job, because quite frankly speaking, so it is not a very complex thing. So all they need to learn, they can even just ignore the bird or the wings, because all birds have wings. All the GANs need to remember is the color. So when we move it to a more complex data set like this one, then it failed miserably. But it have a more complex a language and more diversity in the scene, in the objects that we asked the model to create. So it fails. So and after that, so things kind of did not really move on. And I remember so when I published my book at the end of 2020, so in the last chapter I did some review on this area, and I said, okay, the technology was not there, we are still far away from from even getting close to solving this problem at all. But I remember, so in 2021 in January, then OpenAI, they announced the new architecture called DALL-E. It kind of grabbed the media attention. So the biggest, the most famous, the most iconic images is this one, an avocado shaped chair. So that trains on a very large internet scale of data set, and then the model is good enough to understand what it means, even though these picture have never existed in the data set. So unlike the previously the bird data set, which is a kind of simple, you just have to memorize it. But this one, the model really understood what we mean in the meaning of the text, the semantic meaning of the text, and then generate the image. Okay, so what contributed to this massive improvement? So then we might have to talk about this transformer. So transformer is at the time, so not that new now. It's not new now, but so transformer first introduced into this NLP, which stands for natural language processing. Well, in short, it's words. It works on text, on words. So it is very good in tasks that related to text, and it can understand the meaning of the text well. So one of the previous limitation of the GANs, the GANs only have a simple layers, some very simple layers to try to learn the text, to convert the text into some text embedding. So it also use train on very small image and caption pair dataset like the birds datasets. But DALL-E use a lot of datasets a lot bigger, and also because transformer is very good in learning the meaning of the text, that's why it works very well. So one of the thing that the breakthrough that they did was that because text and image are inherently a different modality, so text we see that as a discrete thing. So it's a word. Just check, for example, chair is a chair. We just say, okay, chair is a chair. But in an image, we can break everything down into a pixel level, right? So in a chair, so we have many pixel. So the pixel have the image of like is represented by a color value. Say from 0, then it is black. To 255 is white. So different color means represent different color, and we see that as a continuous, not a discrete. So at the time, so try DALL-E use another separate image encoder to encode this image into some discrete image tokens. So essentially, we just gonna break that down into grids, okay, and then each grid is represented by a token. So then it reframes the problem. Now text and image are both tokens. So we can just use that to do a prediction from the text. So autoregressive means it tries to predict from auto means self. So it tries to predict from itself. So in this case, it tries to predict the image from the text and also the image before. So in the prediction, we first predict this from the using the text as a constraint, and then we predict the first square here. Okay, and then we use this one as a constraint after we predict this one, and then we predict the next one. So we go left to right and then top to the bottom. So the one of the limitation is that due to this inefficiency in transformer, it is very computation expensive. Whenever you increase the token size, that means if you want to increase the resolution of the image, and if we just need to double it, but because when we double times 2, so this side we times 2, the other side also times 2, so altogether is times 4, and the complexity of transformer like quadruple, mean is square. So if we double the image resolution, we actually have to have 16 times more computation and power and memory. So for this reason, so the DALL-E result it is in low resolution. It's only I think 256, because it's very difficult to increase the resolution. And the other weakness of this DALL-E is that it is not very good at predicting or knowing which the property relates to which object. So for example, in this case, it's a stack of 3 cubes. So by the way, this example taken from this the DALL-E website. So it's supposed to have 3 cubes. The red cube is on top, and then the second is green tube, and then there's a blue tube. The last is blue cubes. So it is able to produce cubes with various color, but they are not in the exact same order, and they are not they do not have the exact same number of cubes either. So this is one thing that DALL-E is not doing very well. So it was introduced in like 2021. I think for a long time, for about a year. So there was no alternative architecture. So there are some variant of transformer base, but this was the state of the art. And then things changed with our third generation algorithm, which we call diffusion model. So it started really. So this diffusion model is not new. It was introduced I think in 2016-ish, but only starting from 2020. So people have the researcher have worked to make this model really works to produce image that have good quality. And then after that, things just move on very, very quickly. In 2021, so they produce the researcher published a paper that said, okay, that claim that our result finally is able to beat GANs. Okay, after that, everything just exploded. So, now we can create image that looks very very good. It have almost no weakness to me, right? When I look at it today, so the image looks perfect. There are some minor thing is that it takes a long time to train and inference, blah blah blah. But that is you don't see it. We only see the results. So these are currently there are these three models that that produce very good result. I think most people probably have heard of DALL-E 2 from OpenAI, and the latest one and greatest state of the art is the Google's Imagen. So although OpenAI they actually did have another model that came before DALL-E 2, is called Glide, but it was not as well known as DALL-E 2, maybe probably because its predecessor, the DALL-E, is more famous, and then it's just get more exposure in the media. So the example here I posted here are from this Google website. So if I encourage you to just go to the website to look at a lot more high quality, high resolution images. So like what amazed me the most is that this one looks totally legitimate. So it's a painting of Raccoon Queen, okay, wearing a red French royal gown. So and then even describe to even go further to describe that it's hanging on a wall decorated with wallpaper. So this looks amazing to me. So here are more examples, like a teddy bear swimming, and a corgi live in the house made out of sushi. Okay, all right, and there are many weird things. You can also look at this DALL-E 2 website. They also have some examples which also look quite good. All right, so okay, finally we can start looking into what is this diffusion model is about. Okay, so the full name of diffusion measure is known as denoising diffusion probabilistic models, but we just call diffusion model for short. So as the name suggests, denoising, so the model is supposed to denoise, which is to remove the noise. So what does it mean? So when we do the training, it's quite simple. We just take an image. By the way, this is my picture. We just keep adding noise. Okay, so this is scale. We scale it to make it not to scale the resolution, but scale the pixel value to be smaller, so that when we add noise, it doesn't get saturated. So what I mean by that, so the pixel is represented by a value from 0 to 255. So 255 is the maximum. If we add anything to that, more than that, okay, say we add 1 or we add 10, we will actually clip that to 255. So if we add some noise, because noise can be, we now assume that noise is from 0 to 255, or some small values. Let's say we assume the noise is like -2 to -2 to +2. So mean if it is 2, we add a 255, then that can become saturated. It will clip that to 255. If we do not scale this one, we just keep adding noise, eventually every value will be 255, and we got a white image and we lose all the information. So this is why we do this scaling. So the forward diffusion model is just to keep adding noise, scale and add noise, repeat that for many steps, like 1,000 steps, and eventually you get this noise. Okay, sound like fairly straightforward. But then how do we generate image. So we do the reverse. We call it reverse diffusion, or we call it sampling with inference. So we start from the right. So we create a noise. Okay, we use a Gaussian noise, and then we move backwards. We do the reverse. So we just minus the noise here, and then do the scaling. Then keep doing it, and then we will reach this state, the good image. All right. So it really is that simple. Well, of course, you it's not that you cannot just add any random noise, because when we do the reverse step, the noise have to be a particular type probability of noise that can fit that is able to like recreate the imagery that we want. So let's talk about this noise a little bit. In GANs, the assumption is that the whole image can be represented with like smaller dimension of a latent variable. So if we take this guy human face as an example, we don't need to know like every single pixel to fully describe what is in the picture, because like humans we have two eyes, one nose, one mouth. They're almost always in a similar kind of location. So instead of labeling every single pixel, in GAN we can have some small number of latent variable to say that okay, so this is the color of the eye, the size of the eyes, whether the expression, how the gender, there may be another variable to say it's gender, or the age, etc. But different in that the diffusion model, so every single pixel is a latent variable itself. You can see that as a latent variable. So it has a very high dimensional latent variable, a very high dimensional space. So I think maybe because of this is a reason, so it can create a more detailed image. Okay, if you do a comparison, so they can, especially the texture part, so they can create really very fine texture using diffusion model compared to GANs, and it also can able to capture richer like content, like more diverse content. So GANs, what we can see now, although GANs we can create like very photorealistic image with style GAN or its variants, but it limits to that face dataset. You can train it on a separate dataset, but it won't work. It won't really work if you try to use it to try to predict say 1000 clusters of image there, or to that high resolution. I haven't seen any people done that. Maybe there's, but I haven't seen that. So this is the advantage of a diffusion model. Okay, let me recap. Okay, so diffusion model to train, just keep adding noise. To do the sampling, we do the reverse. Okay, the diffusion model is actually quite simple to explain, although the math is difficult. But it is relatively easier compared to GANs. So with GANs, I need to write one book, entire book, just to get you to state of the art, because there are many little things to the art and you should learn gradually to build up your knowledge to eventually create a complex model. But for diffusion model, it is actually not the implementation, the model architecture is not that difficult. The math is, but when the math is done, divided by this researcher, when it comes down to implementation, it is quite simple, and I could like introduce you the model to state of the art in 1 hour talks. Where each for GAN is not possible. Yeah, I need many hours to do that. Okay, so the main two things you need to know about diffusion you can see that I see that into two different blocks of things that you need to learn, and they are quite separate, so you can look at them separately. So the first part is the noise schedule or the variance schedule. This controls how much noise we add in every step and how many steps. So typically we use 1000 steps. So the noise here at different step is different. So different level of noise. So we want to say in the very beginning we only add a little bit of noise, and so gradually as we move on we add more noise. So the one of the basic schedule is we call a linear schedule. We just add the noise linearly from like fewer and then to the more noise. Then the other one is called cosine. Cosine is looks so in the middle steps they are quite similar to the linear, but they have less noise. The increase of noise is less towards the both ends. So this was introduced by OpenAI, and also OpenAI also use another method that is, instead of fixed variance schedule, you can train a neural network to try to learn how much noise to use. So for simplicity, I think you can just assume, say, making simple, is a linear noise, so linear schedule. So this part is quite messy, so there are a lot of math to derive to come up with how much noise you should add. And in general, people don't really change this part. They just reuse the schedule. And most of the innovation actually happened in here. UNet. So after we do this one, after we do the for diffusion, and when we do the reverse diffusion, we cannot just minus any random noise. We have to, as I mentioned, so we have to subtract the particular noise. So how do we do that? So we use a neural network to predict the noise, and that neural network architecture is called UNet. So UNet, let me go skip to this slide. In other words, just look at this diagram. So this is the diagram of a UNet, just a high level one. So high level description. So the UNet have a same dimensional input and output. So in this case, it's same size. So this is an image of 128 by 128 pixel. The output is the same. So in the UNet, when there's a part that do this encoding, it gradually reduces the feature map size, and then it expand. And for every feature map size, there's a skip connection, so they can pass the information. So what the job of this UNet in here is to, you send in a noisy image, which is this one. This is the noisy image. So this is the input, and then the output is this. So the UNet will try to predict the noise that for you to use, right? So UNet, function of UNet takes in noisy image and the time step. Why do we need to pass in a time step to the UNet? That is because, like I mentioned, this we have this variance schedule. So every time step uses a different noise. So that's why the UNet need to know which time step so it can work out. So what kind of a noise level it will need to produce. Okay. Right. So how does the UNet make use of time step? The time step, or it just basically take a time step. Say if 1, and then it project into embedding, and then they just insert the embedding into one of the layers inside UNet. So that's what how it condition, how they do the conditioning. So most of the interesting innovation in the paper. So the first part, the variance schedule, is you can reuse that. So a lot of the interesting thing happens in or around the UNets where you do the condition. So what I mean by that, so when we have this diffusion model, if we train it on human on the faces, then we create a noise. Then if we do the sampling, then it will create a human faces. But we do not have control about what people, the look of the people we want it to create. So there is nothing we can control. That's why we need to be able to specify what we want it to control. We have to use these extra conditions. For example, you can use image, or you can use text. And we will go to the next slide. We will not yet. So before we delve into the UNets, I will we will look at the algorithm from the paper on how to train it. So this slide includes everything you need to know to do the training steps. So the first step, let's look at the algorithm one. I will go line by line and then try to explain it. Okay. So line 2, X naught, you sample from a data set. So if you sample from face data set, so this is my X naught. And then we sample a T from a time step is 1 to 1000. And then we create a random Gaussian noise. Gaussian is normal distribution, also is a Gaussian distribution. So this is that means the noise in every pixel, they are independent to each other. So it's a random Gaussian noise. Right. And then we look at this term. So this is the term that we want to the loss term. This is the loss function. So this epsilon theta. So theta is the parameter, which is the parameters of this UNet. So this one, circled in blue, is a UNet. So UNet takes in two parameters. T is a time step, like I have described. Okay, UNet take noisy image and time step. So this is a noisy image. So what means is that, so this is a scale version, you make it smaller, and then you add some noise. So this is the noise schedule. So just to note that, so this alpha T is actually alpha hat T. So the value is different for each time step. It is not the same. So when the T is small, say as a T equals to 1, so this one is a high number, so it's very close to 1. And then this one when this one is close to 1, so this one will be like the whole term is close to 0. That means we have less noise. As we move on to more T, then this scale will be bigger. I mean the image will be the value will scale be smaller, and then the noise increase. Okay, and although that we do we look at this picture, the diagram is a Markov chain. That means we have to go step by step. But after some derivation of this equation, so we do not need to do the training take step by step. We can take any of the time step and then use this equation to work out the how much scale that we want to apply from this image and how much noise we want to add for this step. So in other words, in a mini batch, it's a random batch of time step. For example, it can run at 5, 10, 20, 17. So that form a mini batch to train. And after the UNet, so this one is the UNet. It takes the scale, noisy image, and the time step to predict a noise. And then the next step, the loss function, is simple. We just do a L2 loss between the predicted noise and the random noise. And then we just keep doing it until it converges. Okay. So that is the training. So during the inference, algorithm 2, we do the reverse. For the reverse, we start from right hand side. We first create a noise. Okay, we just xt. So xt is the big T. Okay, big T is here. And then you just do a reverse and apply this equation. So the equation, we just look at this one. We look at this one first. So if theta is a unit, so we take the noisy image and the time step, and we predict the noise. Okay, so we predict the noise. So this is the predicted noise. We do some scaling, and then we subtract. So here, see if you compare these two equations. So this one is to add the noise, and this one you just subtract the noise. Okay, so it is not it's not really the derivation is use some Bayesian to derive, but roughly you can see that this one is a plus, this one is a minus, and there's some different scaling. And there's also this term is to add the noise. So it comes from the math class, but as we understand it from high level, to train, scale, and add noise, and then to do the sampling, we do it reverse. So we get a noise and scale, and then subtract the noise from the noisy image. Then the image become less and less noisy, and then finally create very crispy images. So these are the basic algorithms that this is the algorithm you need to know to train the diffusion model. All right. Okay. Next, we will talk about this how to use the one application of diffusion model, and one of the early application is to use super resolution. Super resolution means that you increase the image resolution by a lot. So in conventional, before deep learning, so in conventional like image processing, in order to increase the resolution so of this picture of picture, we will just take the picture. Like for example, we take the picture and then create an image with an array or a matrix with a higher resolution. We just place the picture into the location, and then we do the interpolation between the pixel. So the result tend to be blurry, like what we see with this input. So this is low resolution images. We upscale it, just by doing interpolation into a higher resolution. And this is the result that we want to get. This is the result on the right hand side is the result that we want to get with a high resolution image. Then how do we do that with diffusion model? Right, every step is the same as before. Same equation. You just add noise and then subtract noise. The only difference that now we add the condition to the unit, and the condition is this blurry image. This is also our input to our our algorithm. So when we do the training, the part that pass in the noisy image into unit, the only thing extra is that at the input, so originally, so this YT is the noisy image. It try to predict the noise. The difference is that we add a image condition, which is this image, to the input of the unit. So in every time step, we just add this one. The rest is the same, so we just have noisy input in every time step. But every time step, we concatenate this blurry image into here as a condition. So it is just that simple, and then it works well. Okay, you don't need to change the rest of the thing, all the equation or everything same. The only thing is that now you add this extra image as a condition by concatenating with this thing. I think the author of the paper, they say you can try to do other methods or other way of embedding. You can like perhaps put this one inside here, but they found this works, and then they didn't have to like change the unit architecture. It works well. And these have a very kind of like profound impact on the image quality as we see from this DALL-E 2 and Google's Imagen. Nowadays, the diffusion model, when they come to image generation, it comes with two stage. So one is to use diffusion model to generate a low resolution images, because it will be like easier to train, because the output is smaller, than everything string. Again, you can train it faster with more data. But after that, you train a separate diffusion model to do super resolution. And one good thing about this one is that you can do that in different stages, and then you cascade them together to increase the resolution by stages. So then you can train this different resolution of like super resolution diffusion model separately. So one to increase it from, for example, from 128 to 5112, then the other one from 5112 to 1024, etc. Yeah, so that is one of the reason why, if we go back to comparing, from here, DALL-E 2 to now, only like 1 year. After 1 year, the image quality improved massively. One of the reason is the super resolution provided by diffusion model. Okay. Right. Okay. Finally, finally we're going to talk about text. How do we use text? So the super resolution we see just now, we use an image as a condition. So now we want to use a text as a condition. So there are two ways of doing that. So the first one is called classifier guidance. The second one is called classifier-free guidance. Of course, in order to understand what is classifier-free, we have to understand what we mean by classifier guidance. So the classifier guidance was introduced in that paper. They try to do an experiment to train on ImageNet. So ImageNet, as we know, there are like 1,000 different classes. So the researchers found that by using this, although previously they already project this class embedding into these normalization layers in the UNet. So before this classifier, they already did that. But what they found that they could further improve the image quality by training a separate classifier. So in this case, in addition to a diffusion model, so there is another classifier. So just a normal CNN like ResNet to do the classification of this ImageNet. So they train that classifier with this noisy image, because as we know, when we do this diffusion model, every step is getting noisy. But if you use just a vanilla off-the-shelf classifier, so it may not work that well when we fit in the noisy image. So you train in every time step, we show the noisy image to the classifier, and then it will give a loss function, the softmax of the classes, and then we back propagate the gradient to the image. So not to the weight of the classifier, but to the weight of the input, which is the noisy image. So this is the equation, a simplified equation. So the noise here is the noise we use in our previous slide. So the noise that is predicted by the output of the UNet. So after we get the output of the UNet, the noise, we add a new term here. we start from this right one. So this one is the gradient of the classifier. So the classifier gradient backprop to the noisy image. So this will have the same dimension as the image. And then this is the noise variance schedule for that time step. And then this one is the guidance scale. So we can see that the guidance scale as the weights, how much we want to emphasize the class information. So if we use a higher weight, it can produce higher quality image that is that matches the text or the class, the classes or the text description more, but at the expense of this diversity. So maybe it will create less diverse because we set the weight to be high to the particular class. And one example of how we use that in this text to image generation is that we, instead of using a class label, we use the creep loss to do this backpropagation. I will elaborate on this one about creeps. If you're not familiar, I will elaborate that in a later slide. So that is the classifier guidance. Then subsequent research found that it actually works better with the other method, which is called classifier-free guidance. That means we do not need to train a separate classifier just to we don't need to train a separate classifier. We only need to do it with the UNet. We just only need to modify the UNet. So that's how we do it. So let's say text embedding. Text embedding is just some vector. You can get this text embedding with various different methods. You can use a transformer. You can use a different neural network. You can there are many ways to train to get a text embedding. Basically, it's just a vector. So if we get the input text, text caption, we convert that into a text embedding, and then we insert that into UNet, one of the attention layers. We can put that in other layers. So that means that we create a text. Say I'm a dog. Okay, there is a dog. So that dog convert into some vector. You can put the embedding inside here. There are various way of doing that. You can concatenate. You can add to some of the things. You can multiply. You can there are different ways. But the key thing is that you inject the embedding inside the UNet so that it can use that as a condition. So in this modified UNet, the UNet accept this text embedding. But occasionally, occasionally we pass in a null label in training. That means condition on nothing. So assuming there's no there's a null embedding, maybe just a vector of 0. So occasionally we use that, put in a null, and then we condition on the label on your text. Okay, so this is the noise with this text embedding. So this is the noise without text embedding. We think of neutral. So if we imagine, let's say it's not text. Let's say it's an image. So this let's imagine say, so this is without, now is my face, the neutral face. I'm not smiling. Let's say this white is smile. Okay, so this is the mouth. That is the face that I'm smiling. So the minus here, so smile minus neutral. That means you try to find the direction of the smile attribute. And then we use this scale, is a knob to turn that up. So if you want me to smile happier, we mouth open bigger, we increase the S. So if we compare this and this, they're actually the first part is here. So this is the noise without anything, just a normal noise. So this is the S. So we replace this one with this with this the difference between of the noise with condition, and this one without condition. Okay, so by doing that, we can use this one to inject, okay, the text embedding we want, and then we can use that to create the images. Okay, next, okay, this slide. So this is the last slide that with some equation, and that so we have learned all the essential things to be able to allow us to understand the state-of-the-art models. So one of the big difference between all these models, right, are actually in how they create this text embedding. So if we learn from DALL-E 1, right, so one of the thing that result in massive improvement from DALL-E 1 from GAN to DALL-E 1 is the use of transformer. So we know transformer is very good in learning about text. So one natural choice is that we feed the data, a text, into a transformer that already pre-trained on image task, on this guy on text, and then get the embedding from this transformer. So you set in an input, so transformer will create some output and embedding. So we use the embedding and put that into our unit. So this is the method that is used by a glide. And then DALL-E 2 claimed to beat glide using different method, but later ImageNet beat both of them. But the Imagen is using a very similar architecture. The method is actually very similar with glide. So it also uses a transformer to create this text embedding. The difference is that it uses a much bigger transformer to do. So glide a smaller one. So Google being Google, they just try to outside the competitors. They try to put in the biggest transformer they have, because they already have training for other tasks, for the NLP task. So they put in the transformer, and then it improves the result. So what note on that is that they also try to they also make some improvement to the unit to make it faster to train. They change the architecture to improve it, but they found that using a bigger transformer have bigger impact in the image quality. All right, so that's the first one. The second one used by DALL-E 2 is image prior. Now we can talk about the crypt. So previously we talked about the crypt for classifier guidance. Now this slide is come from this DALL-E. We look at this dotted line here. So the top parts describe what the crypt is. So for the crypt, there are two parts. So one is the text. The input, there will be text. So it trains on text and image pair. Text and image. So for every image, there's a corresponding text that describe what it is, or describe the image. So it first project encodes into some embedding, the text. Then there is a separate image encoder that encode this image into an embedding. Then the training, the model will try to use this guy's similarity loss to try to make these two embedding very close to each other. So after the training, so these two should create embedding that is looks very close in distance, in Euclidean distance. That means they are very close in meaning. It's a semantic meaning. But it turned out that they found that so instead of using this text embedding to put that into diffusion model, they found it is better to actually use an image embedding. So they did another step, additional step, that is to train another model here, okay, to convert text embedding into image embedding before feeding into this diffusion model. So that decoder is a diffusion model. So, well, this is not important. These two lines mean they try two different methods. So this one method is to use transformer to do autoregressive. The other one is to use a diffusion model to do this application from text to image embedding. I think some they found it image to be better. Maybe like the phrase say one image is better than 1,000 words. So there may be something that is better encoded, represented by the image rather than words. So they do it. But then I think later Google said that Google just used the text embedding from transformer, and they produce a good result. So I was thinking maybe this step not really necessary if you have a bigger transformer. Okay. Now, okay, then we compare. So it may compare between these Google and the OpenAI model. Google's models came out just, I think, a few weeks, 2 to 3 weeks, a few weeks after DALL-E 2. And Imagen claimed to beat DALL-E 2. So one thing that it does exceptionally well is that it can associate the property to the object very good. If you look at this bottom image, so we can see that the text prompt is a black apple and a green pear. Well, we know in the real world there is really no black apple. We have green apple and black backpack. So we understand when we put that in this sentence that the black refer to the apple, and then green to backpack. But DALL-E doesn't quite get that quite well. It kind of say, they kind of think that okay, apple is more natural to like represent the apple, so it create a green apple instead. But well, for Imagen, and then I think probably because of this the big transformer model, the transformer is able to understand this association. So black apple means the apple that's black, and able to create that quite faithfully. Same goes for the image on top. So it's a yellow book and a red wasp. So yellow book, red wasp, but DALL-E 2 got it wrong. So this is the same limitation that we seen with this DALL-E 1. So potentially, because DALL-E 1 used transformer, DALL-E 2 uses diffusion model, so the underlying architecture is different. But one thing that share the same is that they these two actually no. So I was thinking, so maybe because it's the limitation of creep. So the creep is not trained well enough. Because the creep require an image and caption pair. So that set a limitation of the data set size. While Google, the transformer trains solely on this text. It doesn't require any image to do a training. So because of that, so it can use a bigger transformer to train on much bigger text dataset to better understand the semantic meaning of the text. So perhaps that's a reason why the Google's methods outperform DALL-E 2 because of this crypt limitation in crypt. Right. So if you are interested in trying, okay, bad news is that Google say Imagen is not for sale. They do not plan to open to the public. But for DALL-E 2, it's typo, it should be DALL-E 2. So DALL-E 2, there is a waitlist you can join. Then they will they may give you to have a go to try the model. So the plan is obvious. The OpenAI will try to commercialize them. So will open up some API that you can pay and then use the services. So if you are just want to have a feel, okay, of how this thing works, there are a few things you can a few open source model or demo you can try. So the first one is I'll just introduce them briefly before we try to open them and to have a go. So DALL-E Mini is based on DALL-E 1. It is created by Hugging Face. You don't need to do any setup. Go to the website, type in the text, it will generate some results. The drawback is that often when I try it, depend on the time you try. So sometimes the server is always busy. You will not be able to get access to it. Okay, then we talk about this OpenAI guide. So they train mini versions. When they do so they train it using a smaller model, smaller diffusion model. They use a smaller data set, so smaller resolution, so the result do not look very good, but it is fast. So this one is fast. There's one thing I probably should mention. So when we do the sampling, we do step by step. We have to do 1,000 steps in just in order to create the image. So that is the reason why it is slow. So if you try to run this one, okay, DiscoDiffusion, it is quite slow. Okay, you will have to wait 15 minutes or so just to create one image, because it goes step by step. OpenAI actually use a different algorithm in sampling where it can skip the step. So I did not cover that in this presentation. So this makes the sampling faster. Okay, like mentioned, so this is just a low resolution demo just to get a feel. This one, DiscoDiffusion, is something you can create high resolution image, like the one I used on the first slide. The background is created from DiscoDiffusion. It's an open source model. It uses the crypt guidance, a classifier guidance. Now we will just briefly, okay, we'll go to look at each of the demo. So the DALL-E Mini demo. So this is something I just tried in this morning. It showed this result. Mad scientist giving a talk about artificial intelligence going to destroy the world, and it creates some mad scientist images. Okay, so they are quite blurry because it is trained on with a smaller data set and small GPU. So we do not expect it to have a high realistic photorealistic quality, but you can play with it. But just remember, this is a small version. This is not what the state-of-the-art model is capable of doing. Okay, so you can just type in things and then click run. If it doesn't say traffic is busy, then you wait a minute or so and you will come up with some result. And the other thing is that let's see. Okay, we can look at this glide. Right, okay. Glide is faster to run, so we will run this one. Show you. So all you need to do is click on the link, and then you should have a Google account. It will give you some access to a free collab that is basically Jupyter Notebook on the cloud that you can run for free. By default, it will set to use. I think it will set to use a GPU. So you just, for this one, it's very simple. You just run everything. Okay, I will just run everything and then we'll go through the code a little bit. It is a very quite straightforward, simple code. Alright, so this one, so it's the text prompt, or we can call text condition, but normally so we use text prompt because we don't necessarily follow what you ask it to do. That's why it's only a prompt. So it's not a command, it's not an order. And this is the guidance scale, the S. You remember the S that we taught in the slide. So they use this tree as the guidance for how much we want the text to mean. Okay, to guide the direction of the text of the image towards the text. So now it is trying to the first time you run, it will download and create. It will download the model here. So it's now downloading from the server to the Google Colab server. Okay, how many? Okay, it should be soon. Okay. So the first step here, the model will encode the text prompt into a token. Okay, I remember Glide uses a transformer, so it tokenizes this thing and then add some padding. Okay, alright, so this is the model function. Right, well, let's not delve into this one. We just look at the command. So this one is a classifier-free guidance. Okay, it uses classifier-free guidance. Now we know what classifier-free means. Okay, and then this is the step, diffusion loops. So there's a loop. I mean, you create this step. So there are multiple steps. You run multiple steps to create an image. Right, so let's wait. How long more? Okay, should be soon. Right. Oh, battery low. Okay, done. Oh no, it is trying to. Okay. Right, so while we wait, I will just jump onto this DiscoDiffusion model. So this one it will take even longer to run. So I won't run it. Just for your information, there are many people. They are constantly showing the result of their model, like the painting, the art that you can actually look at. On Twitter, you can try to find some Twitter account, like let me see. Okay, it's one. Okay, for example, so there is this guy. Okay, it's a weird DALL-E generation. It show you some of the text prompt that some user on Reddit asked them to try. Okay, some are quite hilarious, some are quite real. Okay, so this one, Obama making a sandcastle. Okay, so you can get a feel of like this. So this one is DALL-E. There are other one that use a diffusion model. Okay. So let's go back to our. It's not done. Okay, DiscoDiffusion. So if you were to run this one, I would just you can just use the default setting. I just uncheck this Google Drive and save model to Google Drive because I don't want the hassle of connecting to my Google Drive. If I just want to have a quick play around with this one. So this difficult model is a bigger model, 512. So it can, but the actual image resolution is not limited by this one. You can create a higher resolution image. You just click everything and then run. So one thing that is different is that it uses a lot of a different clip model of different configuration they claim to be able to, by using more, you can improve the what they call the image quality. So I think I forgot to mention this one. So this one uses a crypt, using crypt as a classifier guidance. So it compare the result, the generation result of diffusion model, and then compare with the embedding of the text, and then use it as a loss to backpropagate to guide the model. Okay, so if you just follow this one and run, and then you just wait, and then the other one of the things that you might want to change is that the end batches. If you just want to generate one image to try, you just change this one into one, so it will be faster. Otherwise, you wonder, well, why it takes so long, but it actually is that it just repeat this one, the process for 50 times. Right, now we can now go back to look at our mini glide, or glide mini. Alright, there we go. So this is the small image. How, I think it's only 30, I'm not sure the resolution, I think 32 by 32 or 16, I think 32 by 32. Then we have another explanation. So nowadays they have two stages. You generate a low resolution, then you use another model to upsample it. So yeah, so we can maybe try. So after initially it takes a long time only to download all the models. After that is actually, for this one, it's quite fast to run. We can try to edit tag an oil painting of Koji sleeping in snow. Okay, let's say. Okay, we run it. So it only use 100 steps compared to 1000 steps. So this one faster, and because it's low resolution, so it is quite fast. Okay, there you go. And then upsample. Ta-da! Okay, so for this one, this glide mini, although the results are not great, but it's fast to run and you don't have to wait for the server traffic, and so I would recommend you to have a go. Okay, so in the last slide, okay, because we're not doing, so I'm original, so make this presentation for a conference, for Open Data Science conference. So there was a Q&A. Obviously I can do Q&A now. So if you have any question or you want to connect with me, feel free to add me on LinkedIn. Just mention about you've seen this video. Feel free to collaborate if you have any idea or any project or any training that I may be able to help. Okay. Once again, thank you for watching. Okay, bye.